Welcome to T2, day 11 of calculus. We're going to take a deeper look at the derivatives of trig functions. We're going to start by looking at the derivative of tangent. We're going to determine first what is the derivative of tangent. So the first thing you do is you rewrite tangent as its sine and cosine definition, which is tangent is sine over cosine. And now what we're going to do is we're going to take the derivative of this quotient. We're going to use the quotient rule, which remember is low d high minus high d low over low squared. So in this case, f prime of x, low cosine low d high, derivative of sine is cosine low d high, minus high d low, the derivative of cosine is negative sine of x, all over low squared cosine squared x. So what you end up with when you clean this up a little, you end up with cosine squared plus sine squared. Remember you have the two negatives out there, so it turns into plus. So you have cosine squared plus sine squared over cosine squared. Cosine squared plus sine squared, this is a trig identity. Cosine squared plus sine squared is always equal to 1, so this is equal to 1 over cosine squared of x. And by definition, 1 over cosine is secant. 1 over cosine is secant, so this is just going to be secant squared x. So what that tells you is that the derivative of tangent is secant squared, So now let's find out what the derivative of the natural log of x is. And to start this one, you have to start with what seems like a trick, but e to the ln x is equal to x. This is kind of a random start, but it's really important. E to the ln x is equal to x. That's just a truth. It's kind of like this. It's a to the log base a of x is always equal to x. So in this case, e and e, well, log base e is ln. So you start with this truth right here. You start with this truth. And then what you're going to do is you're going to take the derivative with respect of both sides. So if you do that, you know it's going to be ln of e times, we know that's 1, but times e to the ln x times, because of the chain rule, the derivative of ln x, because that's in the exponent. Well, the derivative of just x is 1. And we know that this is 1. So if we clean it up a little bit, we have e to the ln x times the derivative d dx of ln x is equal to 1. Well, we know from our original statement e to the ln x equals x. So this right here is equal to x. So we know that x d dx of ln x is equal to 1. So this tells us that d dx, the derivative of ln x, is equal to 1 over x. So what this tells you is f prime, when f is ln x, is 1 over x. So you don't have to prove this every time you use it. You can just say, if I ever ask you for the derivative of ln x, if the derivative is 1 over x. This is something you need to memorize. Similar to the derivative of tangent is secant squared. So how does this apply when we're using the chain rule? Well, when we're doing the derivative here, the outer function is tangent, and we know the derivative of tangent is secant squared. So you do secant squared of 2x squared plus 4x plus 1. But now, because of the chain rule, you need to multiply by the derivative of the inside. So the chain rule tells us that we have to multiply by the derivative of the inside. So that's going to be the derivative of 2x squared plus 4x plus 1. So it'll be 4x plus 4. And you can leave it just like that. What about this one? We have to use the product rule here. So in this case, g prime is going to be the derivative of the first, which is secant squared. And that's going to be multiplied by the second, sine of x. So derivative of the first times the second, plus the first times the derivative of the second. Derivative sine is cosine x. And you can leave it like that. That's as far as I want you to go right now. What about this? Well, we know that the derivative of ln is 1 over x, but it's not x this time. It's something else. So we're going to have to use the chain rule. So in this case, f prime of x will be not 1 over x, it will be 1 over 2x squared. But then we need to multiply by the derivative there because of the chain rule. The derivative of 2x squared is indeed 4x. And this you can simplify a little bit. This is going to be 4x over 2x squared. So that's just going to simplify to 2 over x. So when the simplification is relatively straightforward, you can do it. But right now I'm looking for this step. That's the big one, that you get the chain rule in there as well. So here's the product of two things. We have the first one and we have the second one. So we're going to have to use the product rule. So h prime of x will be the derivative of the first, so 6x squared, times the second. I like judicious use of parentheses, plus the first times the derivative of the second. Well, the derivative of ln is 1 over the thing, so 2x plus 1 but then you have to use the chain rule here because we have a function inside, not just x. So it's going to be multiplied by 2 because that's the derivative here. That means we're using the chain rule right here. So we use the chain rule inside the product rule. And you could multiply the 2 and the 2, but right now I'm just looking for you to stop right there. That shows me you can run this derivative properly. So in this one, the -4 is just along for the ride. We have a function inside a function inside a function. So cosine ln of 2x plus 1. So we have to use the chain rule twice. So in this case, f prime of x, the -4 is just along for the ride. And what's the derivative of cosine? Well, the derivative of cosine is negative sine times of the inside. But now we need to do the derivative of the inside here. The derivative of the inside there is going to be the derivative of natural log is 1 over the 2x plus 1, but then you have to use the chain rule again and multiply by 2. So the chain rule the first time is here. Oh, that's not the highlighter I wanted to select. You have this right here. That chain rule applied there gives you that part. But then inside the chain rule, you have to do the derivative of this right here. So that right there, and that chain rule derivative right there, the derivative of 2x plus 1, the derivative of 2x plus 1 is just 2. So you had to use the chain rule inside the chain rule. You can clean up the signs just a little bit. You can clean up the signs so you get double negatives. So I would write for final answer 4 sine of ln of 2x plus 1 times 2 over 2x plus 1. That's what I would leave it as right there. You can clean it up just a little, but you don't have to go any further. So now we're finding the equation of a tangent line tangent to that given function at x equals 2. So when it says an exact equation, we need to find the exact slope. So as we've done before, you need to find a point and a slope. Let's do the point first. We're doing it at x equals 2. So we need to do f of 2, and that's going to be 2 times, I'm going to need parentheses there, ln of 2 times 3 is 6 plus 1. So that's going to be 2 times ln 7. You could use your calculator, but you can leave it right like that. That is a number. That is the exact slope. So not exact, so that's the exact y coordinate. So the point we're dealing with is 2 comma 2 ln 7. There's our point. So now for the slope, we need to do the derivative first and then evaluate the derivative at x equals 2. So if prime of x is going to be 2, that's along for the ride, 1 over, because the derivative of natural log is 1 over what's ever in there, 3x plus 1. But then we need to multiply by the derivative of 3x plus 1 because of the chain rule. So what does this mean? The derivative is 6 times 1 over 3x plus 1. So now we need to do f prime of 2. So that's going to be 6 times 1 over 3 times 2 plus 1. So that's going to be 6 over 7. So now we have a point and a slope. So it's going to be y minus 2 ln 7 equals the slope 6/7 times x minus 2. Again, you have the slope marching right there. You have the 2 ln 7, the y coordinate there, and then you have the x1 right there. So that's the exact tangent line. That's the exact tangent line. So just to be super clear, you need to make sure you memorize this, and then you memorize that. You don't need to prove them, but it's nice to know where they come from.